In this section, we discuss semiconductors and the molecular orbitals that best describe the basis of their electronic structure. We will use silicon as our example to describe sp3 orbital hybridization. Silicon is in group 4 of the periodic table and has therefore 4 valence electrons in the 3s and 3p states. Recall that the s orbitals are spherically symmetric, whereas the p orbitals are oriented along a particular direction. These 4 orbitals can hybridize into different basis wave functions because they are relatively similar in energy. Silicon, like carbon, likes to have 4 bonds that are best described by 4 equal sp3 hybrid orbitals. Looking like an asymmetric p orbital, the hybrid sp3 orbital has one major lobe with one phase and a small minor lobe with the opposite phase. The 3p plus 1s states makes a new basis of 4 equal sp3 hybrid orbitals. Each of these 4 hybrid orbitals points along one of the corners of a tetrahedron, enabling tetrahedral bonding in sp3 hybridized systems. The large lobe of the hybrid orbital is now ideally suited to form either bonding interactions with its neighbor or antibonding interactions. For atoms like silicon that make strong covalent bonds, this makes a large energy separation between the bonding and antibonding molecular orbitals. With 4 molecular orbitals participating per atom in bonding, we result in 2 bonding orbitals per atom and 2 antibonding orbitals per atom. In the case of silicon, with 4 electrons per atom, we have an entirely filled bonding molecular orbitals and entirely empty antibonding molecular orbitals, giving us the strongest bonds possible. In a crystal, the bonding molecular orbitals interact weakly with other neighboring bonding molecular orbitals to spread into a filled band that we call the valence band. Similarly, the antibonding molecular orbitals interact with other antibonding molecular orbitals in the crystal to spread into another band which we call the conduction band, and this band now is completely empty for silicon. Recall that in a metal with a Fermi level inside a band, only an infinitesimal amount of energy is required to move an electron from a left moving state to a right moving state, which enables the metal to be a good conductor in an electric field, with electrons at the Fermi level moving from one side to the other. A semiconductor, however, has a Fermi level in a band gap where there are no available electronic states. The electrons are in an entirely filled valence band, while the conduction band is entirely empty. With no electrons, an entirely empty conduction band cannot conduct electrons. However, an entirely filled valence band cannot conduct electrons either. For every left-moving electron, there is a symmetric right-moving electron with the same momentum. Even in an electric potential gradient, there is no flow of electrons from left to right. It's like tilting an entirely filled bottle that doesn't allow water to redistribute from one side of the bottle to the other. Conduction in a semiconductor requires either electrons in the conduction band or spaces in the valence band that allow redistribution of electrons in the valence band. In an intrinsic semiconductor, this can happen through photoexcitation or thermal excitation, where an electron from the valence band is brought above the band gap into the conduction band, but this requires the energy of the band gap for that electron excitation.